welcome to the deep dive. Today, we're going to be exploring adsorption on surfaces.
Okay.
Sounds kind of technical and complicated.
Yeah.
But trust me, it's a really fascinating topic, and we're going to try to make it
Yeah,
as accessible as possible.
definitely.
So we're working with some graduate-level lecture notes on nanocatalysis,
All right.
and those notes go into pretty good depth on this, but they're
Yeah.
a little bit dry.
Okay.
But we're going to try to liven it up a little.
Absolutely.
So basically, we're going to be talking about how molecules stick to surfaces.
Okay.
And this may seem like a really niche topic, but it actually has a
Yeah.
ton of relevance to things you encounter every day.
It's very fundamental.
Yeah, absolutely.
It's everywhere. It's
Yeah.
how materials interact, how your car engine works.
Right.
It's really the invisible dance between molecules and surfaces.
I like the invisible dance.
Yeah.
So let's start with the basics.
Okay.
The lecture notes talk about something called the catalytic cycle. Can you explain what that is?
So the catalytic cycle is essentially a series of steps
Okay.
that describe how a catalyst helps a chemical reaction happen.
Okay.
So it's like a choreographed dance between molecules and the catalyst's surface.
All right. So adsorption is one of the steps in this dance.
It's the first step.
Okay, got it. So it's like the molecules are finding their partners for the dance.
Yes.
Now, I noticed the notes mention two types of adsorption,
Yes.
physisorption and chemisorption. What's the difference?
So physisorption is a weak attraction between the molecule and the surface,
Okay.
and it's driven by van der Waals forces.
Okay.
You can kind of think of those as tiny electrostatic magnets attracting the molecules to each other.
Got it.
But chemisorption, on the other hand, is a much stronger bond.
Okay.
And it involves the sharing or transfer of electrons between the molecule and the surface.
So one is like a quick hello and the other is like a
A chemical romance.
deep connection.
Yeah, a full-blown chemical
Got it.
romance.
Okay. I like that. But why do molecules bother sticking to surfaces in the first place?
Well, it all comes down to energy.
Okay.
Surfaces have a certain amount of free energy, which is essentially the energy available to do work.
Okay.
And by attracting and binding molecules, the surface can actually lower its free energy and become more stable.
So it's like the surface is trying to chill out and sticking to molecules helps it do that.
Exactly. And the fact that adsorption always releases heat tells us that the system is moving towards a lower energy state.
Okay. I remember from chemistry class that heat being released means something's becoming more stable.
Mm-hmm.
But I thought increased stability usually means things are getting more ordered.
Right.
Don't molecules become less free to move around when they stick to a surface?
Yes, you're absolutely right.
Doesn't that decrease entropy?
It does.
Okay.
When a molecule adsorbs onto a surface, its entropy decreases because it loses some of its freedom to move around. But the enthalpy change, the heat released or absorbed during the process, has to be negative enough to offset that decrease in entropy.
So it's like a tug of war between enthalpy and entropy.
Exactly.
And enthalpy has to win out for adsorption to happen.
Yes, and that negative enthalpy change comes from the formation of new bonds.
Okay.
Between the molecule and the surface, those bonds release energy, which is what we experience as heat being released.
Got it. So the energy released from bond formation has to be strong enough to overcome the molecule's desire to roam free.
That's a great way to put it.
Okay. So let's go back to those two types of adsorption, physisorption and chemisorption.
Okay.
Can you give me some real-world examples of where we see these processes in action?
Sure. So let's start with physisorption.
Okay.
Remember those weak van der Waals forces we talked about?
Yes.
Well, they're responsible for things like nitrogen gas sticking to surfaces.
Okay.
It might not sound that exciting, but this phenomenon is actually used to measure the surface area of materials.
Wait, how does that work?
So nitrogen molecules are pretty stable, and they don't like to form strong bonds.
Okay.
So when you expose a material to nitrogen gas, those nitrogen molecules will spread out evenly across the surface, forming a single layer.
Oh.
And by measuring how much nitrogen sticks to the surface, you can calculate the total surface area.
Oh, wow.
It's a clever technique that's used in material science all the time.
Yeah, that's really cool. So even these weak interactions can be useful.
Yes.
What about chemisorption? Where do we see that happening?
Chemisorption is everywhere. Think about the catalytic converter in your car.
Okay.
It uses metals like platinum, palladium, and rhodium to facilitate chemical reactions
Okay.
that convert harmful exhaust gases into less harmful ones.
So those metals are acting as catalysts, and chemisorption is playing a key role in that process.
Absolutely.
Okay.
The exhaust gases, things like carbon monoxide and nitrogen oxides, they chemisorb onto the surface of the catalyst.
Okay.
And this weakens the bonds within those molecules, making it easier for them to react and form less harmful products.
Wow. So it's happening right under our noses, or rather under our cars.
Yeah.
Okay, so we've got these two types of adsorption, and they're both important for different reasons.
Right.
Now, I remember the lecture notes mention something called the Lennard-Jones potential.
Yes.
What exactly is that?
So the Lennard-Jones potential is a mathematical way to describe the interaction energy
Okay,
between a molecule and a surface during physisorption.
okay.
It's like a graph that shows how the energy of the system changes
Okay.
as the molecule gets closer to the surface.
All right, I'm visualizing a graph. What does it look like?
It has this characteristic dip.
Okay.
As the molecule approaches the surface, the attractive van der Waals forces pull it closer, lowering the energy.
Okay.
But if the molecule gets too close,
Yeah.
the electron clouds of the molecule and the surface atoms start to repel each other, causing the energy to shoot up.
So it's like finding the sweet spot, not too close, not too far.
Exactly. That sweet spot where the energy is at its lowest
Okay.
is the equilibrium distance for physisorption.
Got it. So the Lennard-Jones potential helps us understand this delicate balance of forces at play during physisorption.
Right.
Now let's shift gears and talk more about chemisorption. How does that process actually work at the molecular level?
Chemisorption is all about the formation of chemical bonds between the molecule and the surface.
Okay.
This means electrons are being shared or transferred, leading to a redistribution of electron density.
Okay.
It's not just a gentle attraction, it's a true chemical bond.
So it's like the molecule and the surface are becoming one.
In a way, yes, they're forming a new entity with its own unique properties.
Okay.
And because chemical bonds are very specific, chemisorption often involves particular sites on the surface
Okay.
where the molecule prefers to bind.
So it's like finding the right puzzle piece that fits perfectly on the surface.
That's a great analogy.
Okay.
Now, when we're talking about metal surfaces, things get even more interesting.
Okay.
The adsorbate, which is the molecule sticking to the surface, can interact with different facets of the metal.
Facets. So it's not just a flat uniform surface.
Exactly. Think of it like a diamond.
Okay.
When you cut a diamond, you create all these different facets,
Yep. Okay.
each with its own unique arrangement of atoms.
Right.
Metal surfaces are similar. They have different crystallographic planes, which basically means different arrangements of atoms on the surface.
Okay. I'm picturing a microscopic landscape with hills and valleys, and the molecule is trying to find the best place to settle down.
That's a great way to visualize it.
Okay.
And these different arrangements of atoms can influence how the molecule interacts with the surface.
I see. So the topography of the surface matters.
It does.
Now walk me through the process of a molecule going from a physisorbed state to a chemisorbed state.
So imagine a molecule approaching a metal surface. Initially, it might be held loosely by van der Waals forces in a physisorbed state.
Okay.
But as it gets closer, the electron clouds of the molecule and the surface atoms start to overlap. This overlap can lead to the formation of a chemical bond, and the molecule transitions to a chemisorbed state.
So it's like a gradual shift from a casual encounter to a committed relationship.
Exactly, and here's the really cool part.
Okay.
When a molecule becomes chemisorbed, it gets activated.
What do you mean?
The bond between the adsorbate and the surface actually weakens the bonds within the molecule itself.
Wait, so sticking to the surface makes the molecule more reactive?
Precisely.
Wow.
And that's how catalysts work.
Okay.
They provide a surface where molecules can become more reactive,
Yep.
making it easier for them to undergo chemical transformations.
That's amazing. So the surface is like a personal trainer for the molecule, helping it get in shape for the reaction.
I like that analogy.
Okay. Now, I remember the lecture notes mentioned something called adsorption isotherms.
Yes.
What are those and why are they important?
Adsorption isotherms are basically graphs that show us how much of a substance adsorbs onto a surface
Okay.
at a given pressure or concentration.
So they help us quantify the adsorption process.
Exactly. And one of the most widely used adsorption isotherms is the Langmuir isotherm.
Okay. What's special about the Langmuir isotherm?
It's based on a few key assumptions.
Okay.
Adsorption occurs in a monolayer.
Okay.
All the adsorption sites on the surface are identical.
Okay.
There are no interactions between the adsorbed molecules, and the system is at equilibrium.
So it's a simplified model,
Sure.
but it gives us a starting point for understanding absorption behavior.
Exactly, and it turns out to be incredibly useful in practice.
Okay. How so?
For example, the Langmuir isotherm can help us understand how much carbon monoxide will stick to a catalyst surface in a car's catalytic converter.
Okay.
This information is crucial for designing efficient catalysts that can effectively remove harmful pollutants from exhaust gases.
Wow. So it's not just a theoretical concept. It has real-world applications in environmental protection.
Absolutely.
That's really impressive. Now, I'm curious about the actual chemical bonding that takes place during chemisorption. The notes mention something about the band theory of metals. Can you explain what that is?
Sure. So the band theory of metals describes how the atomic orbitals of metal atoms combine. To form bands of energy levels. You can think of these bands as highways for electrons.
Okay, so instead of discrete energy levels, we have these continuous bands.
Exactly.
Okay.
And these bands can be categorized as spans, p bands, and d bands, depending on the type of atomic orbitals that contribute to them.
I remember those terms from chemistry class, but how do these bands relate to chemisorption?
Well, when a molecule approaches a metal surface, its atomic orbitals can interact with the metal's d band.
Okay.
This interaction can lead to the formation of new molecular orbitals called chemisorption orbitals.
So it's like the molecule and the metal are merging their orbitals, creating a new set of energy levels.
Exactly. And these chemisorption orbitals play a key role in determining the strength and nature of the bond between the molecule and the surface.
I see. So it's not just a simple electrostatic attraction. It's a more complex interaction involving the sharing and redistribution of electrons.
Precisely. And one of the key factors that influences this interaction is something called the Fermi level.
Okay, what's the Fermi level?
So the Fermi level is the highest occupied energy level in a metal at absolute zero temperature.
Okay.
You can think of it as the sea level of electrons in the metal.
So it's like the boundary between filled and empty energy levels.
Exactly. And the position of the Fermi level relative to the chemisorption orbitals can have a profound effect on the strength of the bond between the molecule and the surface.
Okay. I'm intrigued. How does that work?
Well, if the bonding chemisorption orbital is below the Fermi level, it will be filled with electrons, leading to a strong bond between the molecule and the surface.
Okay.
On the other hand, if the antibonding chemisorption orbital is above the Fermi level, it will be empty.
Okay.
Also contributing to a strong bond.
So it's like having a stable, happy molecule attached to the surface.
Exactly. But if the antibonding orbital is partially filled, things get a bit more interesting.
Why is that?
Because a partially filled antibonding orbital can weaken the bond between the molecule and the surface, making the molecule more reactive.
So it's like the molecule is on a looser leash, ready to participate in other reactions.
Exactly. And this is a key concept in catalysis.
Okay.
We often want the adsorbate to be bound to the surface, but not too strongly.
Okay.
It needs to be able to react with other molecules.
So it's all about finding the right balance between bonding and reactivity.
You got it.
That makes sense. Now, remember the notes mentioned something called dissociative adsorption. What is that, and how does it relate to everything we've been discussing?
Dissociative adsorption is when a molecule breaks apart as it adsorbs onto a surface.
Okay, that sounds dramatic. Can you give me an example?
Sure. Imagine a hydrogen molecule, H2. Approaching a metal surface. When it gets close enough, the bond between the two hydrogen atoms can weaken, and the molecule can dissociate, leaving two individual hydrogen atoms absorbed on the surface.
So the surface is acting like a molecular divorce lawyer, encouraging the molecule to split up.
That's one way to put it.
Okay.
But yes, the interaction with the surface can facilitate that dissociation process.
Got it. And again, the Fermi level plays a crucial role in determining how easily this dissociation occurs.
It does.
Okay, I'm starting to see a pattern here. The Fermi level seems to be the conductor of the orchestra, dictating how the electrons behave. And how the molecules interact with the surface.
The Fermi level is a fundamental concept in understanding chemisorption. And its role in catalysis.
This is fascinating stuff.
It is.
But I have to admit my brain is starting to feel a bit full.
Okay.
Can we take a quick break and come back to this in a bit?
Of course. Let's regroup and delve deeper into the world of dissociative adsorption and its implications for catalysis in our next session.
Sounds good. All right, so we were talking about dissociative adsorption, where a molecule breaks apart when it adsorbs onto a surface. Can you walk me through how that plays out in a real-world catalytic process?
Absolutely. One of the best examples is the Fischer-Tropsch process. It's a way to convert synthesis gas, which is a mixture of carbon monoxide and hydrogen, into liquid hydrocarbons, like the fuels we use every day.
So it's kind of like turning gas into liquid gold.
You could say that. And the key to this process is carefully controlling how those CO and H2 molecules Adsorb and dissociate
Okay.
on the surface of the catalyst.
It sounds like a delicate dance.
It really is. The choice of catalyst is crucial here.
Okay.
Different metals have different affinities for CO and H2, which can drastically affect the outcome of the reaction.
Okay.
For example, copper, with its fully filled D bands, doesn't easily break apart CO molecules at moderate temperatures.
So copper is kind of like the gentle hand in this process.
Exactly.
Yeah.
That's why copper is a great catalyst for methanol synthesis, where you want to keep those CO molecules intact.
Got it.
But when you need to break those CO molecules apart, you need a different tool in your catalytic toolkit.
Something a little more heavy duty.
Precisely. Metals like iron have a strong affinity for carbon and readily dissociate CO. In fact, iron forms iron carbides on the surface, which play a key role in breaking apart those CO molecules and assembling them into longer hydrocarbon chains. That's why iron is a crucial component of catalysts used in the Fischer-Tropsch process to make liquid fuels.
So depending on what you want to make, you choose a metal that will either encourage those molecules to stay together or break them apart.
You got it. And this is where that Brønsted-Evans-Polanyi BEP relation we talked about earlier comes in handy. Remember, it connects the activation energy for a reaction with the enthalpy change. In the case of dissociation, it means that the stronger those dissociated fragments bind to the surface, the easier it is to break the molecule apart in the first place.
It's like the surface is saying, come on in, you'll be happier here.
That's a great way to think about it. And since metals with fewer d electrons, like iron, bind things like carbon more strongly, they need less of a push to break those CO molecules apart. They naturally drive the reaction toward making those longer hydrocarbon chains.
So by understanding those D-band trends and how different metals interact with different molecules, you can essentially design a catalyst that's tailor-made for a specific reaction.
Absolutely. It's like having a molecular toolbox, and you get to choose the perfect tool for the job based on these principles of adsorption. Pretty cool, right?
It's mind-blowing to think that something as seemingly simple as molecules sticking to a surface can have such a huge impact on things like fuel production. It really highlights how understanding these fundamental concepts can lead to incredible technological advancements.
Absolutely.
So knowing how to tweak those interactions at the molecular level can actually help us address global issues like energy production and pollution.
Exactly. For example, researchers are working on developing new catalysts that can efficiently convert carbon dioxide into useful chemicals and fuels. This could potentially help us mitigate climate change by reducing greenhouse gas emissions.
That's amazing. So these insights into adsorption could actually play a role in creating a more sustainable future.
Absolutely. And it all starts with understanding how those tiny molecules behave when they encounter a surface.
Okay, so we've talked about two main types of adsorption, physisorption and chemisorption. We've seen how these processes play out in real-world applications like measuring surface area and designing catalysts for fuel production. But I'm curious, are there any other fascinating applications of adsorption that we haven't touched on yet?
Oh, there are countless examples. Adsorption plays a critical role in areas like drug delivery, water purification, and even sensors. For instance, scientists are developing porous materials that can selectively absorb pollutants from water, providing a way to clean contaminated water sources.
So it's like having a molecular sponge that can soak up all the bad stuff.
Exactly. And by tailoring the properties of these materials, you can target specific pollutants and remove them effectively.
That's incredible. So it seems like understanding adsorption really opens up a world of possibilities in terms of designing new materials and technologies.
You're absolutely right. The applications are truly vast and constantly expanding as researchers continue to explore this fascinating field. One area that's particularly exciting is the development of sensors that can detect specific molecules based on their adsorption characteristics.
Wait, how does that work?
Imagine a sensor surface that's designed to selectively adsorb a particular molecule, let's say a toxic gas. When that gas comes into contact with the sensor, it binds to the surface, triggering a detectable change in the sensor's properties. This change could be a shift in electrical conductivity, for example, which would signal the presence of the gas.
So it's like a molecular lock and key where only the right molecule can fit into the lock and trigger the sensor.
That's a great analogy. And these types of sensors are being developed for a wide range of applications, from environmental monitoring to medical diagnostics. For instance, there are sensors that can detect glucose levels in blood based on the adsorption of glucose molecules onto a specific surface.
Wow, that's incredible. It seems like the possibilities are endless.
They really are, and as we continue to delve deeper into the nuances of adsorption, we're bound to uncover even more surprising and groundbreaking applications.
Well, I'm eager to hear more. But before we get too carried away with all the exciting possibilities,
Sure.
I want to circle back to something we discussed earlier.
Okay.
The interaction between a molecule's orbitals and the metal's d band during chemisorption.
Right.
Can you elaborate a bit more on how that interaction affects the strength of the bond and the reactivity of the molecule?
Of course, remember we talked about how the position of the Fermi level relative to those chemisorption orbitals plays a key role.
Yes.
If the antibonding orbital ends up partially filled, it weakens the bond between the molecule and the surface. But there's another factor at play here, the width of the d-band.
Okay, remind me what determines the width of the d-band.
The width of the d-band is related to the degree of overlap.
Okay.
Between the d orbitals of neighboring metal atoms, the more overlap, the wider the band.
So it's like a highway with more lanes. The wider the band, the more electrons can flow freely.
That's a great analogy. And this electron flow or delocalization can have a profound effect on the strength of the chemisorption bond.
How so?
Well, a wider d-band means the electrons are more delocalized,
Okay.
which can lead to a weaker interaction with the adsorbit's orbitals.
Okay.
This can result in a weaker chemisorption bond.
So it's kind of counterintuitive. You'd think more overlap would mean a stronger bond, but it actually leads to a weaker interaction.
It can be a bit counterintuitive, but it all comes down to the way those electrons are distributed and how they interact with the adsorbit's orbitals.
Okay.
And this has important implications for catalytic activity.
I see. So how does the d-band width affect a catalyst's performance?
A narrower d-band with less electron delocalization
Okay.
can lead to a stronger interaction with the adsorbit, which can promote bond activation and facilitate chemical reactions.
Okay.
On the other hand, a wider d-band with more electron delocalization can weaken the interaction, leading to a less active catalyst.
So it's like finding the Goldilocks zone for d-band width, not too narrow, not too wide, just right for optimal catalytic activity.
Exactly, and by understanding these subtle electronic effects, we can tailor the properties of catalysts to enhance their performance for specific reactions.
That's incredible. It really highlights the power of understanding these fundamental concepts at the electronic level.
It does.
Now, I know we've been focusing a lot on metal catalysts, but I'm curious, does adsorption play a significant role in other types of materials?
Absolutely. Adsorption is crucial in a wide range of materials, including polymers, ceramics, and even biological systems. For example, in polymers, adsorption can affect properties like adhesion, wettability, and biocompatibility.
So it's not just about metals and catalysts.
Not at all. Adsorption is a ubiquitous phenomenon that influences the behavior of materials in countless ways.
This is fascinating stuff, but my brain is definitely feeling full again. Can we take another break and come back to this later?
Of course, let's regroup and explore some of the broader implications of adsorption in our final segment.
All right, so we've covered a lot of ground already, from physisorption and chemisorption to d-bands and dissociative adsorption. It's amazing to think about how adsorption shapes our world.
It really is, and we've only just begun to explore its implications.
I'm curious, what are some bigger picture implications of adsorption that we haven't touched on yet?
Well, one area where adsorption is becoming increasingly important is nanotechnology. As we create materials at the nanoscale, the surface area to volume ratio increases dramatically.
Okay.
This means surface effects like adsorption become even more dominant in determining the properties of these materials.
So the smaller you go, the more important adsorption becomes.
Exactly, and this has huge implications for designing and developing new nanomaterials with tailored properties.
Like what?
For instance, researchers are creating nanoparticles that can deliver drugs to specific cells in the body.
Wow.
Based on those cells' adsorption characteristics.
So we're talking about using adsorption to fight diseases at the cellular level.
Precisely. And this is just one example of how understanding adsorption can lead to breakthroughs in nanomedicine.
Okay.
Another exciting area is developing self-cleaning surfaces inspired by nature.
Self-cleaning surfaces, like I never have to clean my bathroom again.
Well, maybe not quite that far yet. But scientists are studying the surfaces of plants like lotus leaves, which have an incredible ability to repel water and dirt.
Yeah.
It turns out that the nanoscale structure of those surfaces, combined with their chemical composition, minimizes the contact area with water droplets, causing them to bead up and roll off, carrying dirt particles with them.
So it's like a microscopic slip and slide for water droplets.
Exactly. And researchers are trying to mimic these natural designs to create synthetic materials with similar self-cleaning properties.
So like windows that never get dirty or clothes that repel stains.
Exactly. That would be awesome. It's a great example of how understanding fundamental interactions at the molecular level can inspire innovative solutions to everyday problems.
This has been an incredible deep dive into the world of adsorption. I feel like I've gained a whole new appreciation for these invisible forces that shape the materials and technologies we use every day.
It really shows the power of scientific curiosity and the importance of understanding these fundamental principles that govern our world.
And it all starts with these tiny molecules clinging to surfaces. Who knew something so simple could be so complex and have such far-reaching implications?
It's a beautiful example of how the smallest things can have the biggest impact.
Well said.
Yeah.
Now, before we wrap up, we always like to leave our listeners with something to think about. A thought-provoking question to spark their curiosity and encourage them to keep exploring.
Okay, here's one. Thinking about the different ways that molecules can interact with surfaces, how might adsorption play a role in something like gecko feet sticking to walls?
Ooh, that's a good one. It makes you think about all the invisible forces at work in nature.
It's a fascinating example of how nature has mastered the art of adsorption to achieve these remarkable feats.
Well, folks, there you have it, a deep dive into the captivating world of adsorption. We hope you enjoyed the journey and that you'll continue to explore the fascinating science behind the everyday world.
Keep those minds curious and those questions flowing.
And until next time, happy adsorbing.